These are almost good.
She's going to Churchill Middle School, so it's a little bit intensive, I guess. Does anyone here, did anyone here go to Churchill for middle school? No? Oh, one. Okay.
One. How was it?
It could have been a lot better.
It's like
terrible, but I noticed a decline as I was getting older. And they were leaving stuff unfixed a lot.
Oh, you mean facility-wise?
Facilities and teacher-wise. Just,
Right.
again, you can do a lot worse stuff.
Well, many other middle schools are even worse because they don't have the money and they have to cram more people into the middle
I'm not
schools.
blaming like that. I'm blaming, just the whole education system today. Like lack of funds, lack of volunteers.
Well, they try to get more money from the government by packing more students because they get paid by a per head basis. So they're pushing students out of elementary school, and that's why they're moving 6th grade into middle school in many schools now.
So it's going to be K to 5 instead of K to 6?
Yeah, they want to push more people into the kindergarten or even pre-kindergarten into the elementary schools. So that way they pack a total of more students into the school system given the number of buildings. And therefore they can collect more money. Except the middle schools usually are not set up to handle that many students. So many middle schools, including I think Arden Middle School, they don't even have enough lockers. Yeah, they ran out of lockers. Anyhow, this is where we are at right now. We are at topic 8. We just talked about short-circuited Boolean operators. I mentioned it. I didn't quite explain it, in full detail, and that's what we'll do today, is to explain that part first. After that, we'll also focus on searching, but in this case, in a sorted array. Searching in an unsorted array is not much fun. I mean, there's really nothing you can do about it. You have to start from one end, and you have to keep looking until one of two things happen. Until one of two things happens. Either you find the item that you're looking for, then you can just say, okay, it is in the array, I'm done. Or you hit the end of the array, and there's nothing else that you can search, you can look into anymore, and then you can conclude and say, okay, I have looked through the entire array. What I'm looking for is not in the array. Those are the only two ways to get out of a search algorithm, especially for unsorted arrays. But once you have an array that is sorted, things are actually ordered, you can use a much better algorithm called the binary search algorithm. Some of you may have read it ahead of time, which is great. If not, we'll talk about it, possibly start to talk about it at the end of today's class. Okay, so I'll pass the row sheet, and just to keep track of who is here for today. And then we'll get started with short-circuited Boolean operators. This is a very important topic because this is actually the same, it is common to most modern programming languages. So whether you're programming in PHP, Visual Basic, C, C++, Java, and etc., they all use short-circuited evaluation when it comes to Boolean operators. So we'll get started with our typical example here. And can anyone tell me what this algorithm is doing? Have we seen this before? What is this logic trying to do? It is incorrect. Well, it is actually correct, but what is it doing?
It's trying to look through all the aspects of the array.
It's a search algorithm.
Yeah.
Okay, it's a search algorithm, which is something that we talked about last Thursday. Okay, it's basically the same algorithm, except this one is actually correct. So what we have here is we have a very typical pattern here. We have I initialized to either a 0 or 1, so that we begin from the first part of the array. And then we have inside the loop, we increment I, which basically means move on to the next element, and we want to take a look at the next element. We also have a very, very typical condition in the while loop here, which is I is less than bar a bar. Because as long as I start with 0, and as long as it is less than bar a bar, it means I is a valid index into the array. Does everybody still remember what is a valid index into an array? It's a number that can identify an element in an array. That number goes from 0 all the way up to bar A bar minus 1. What is bar A bar? The number of elements. Okay, so in this class, I just use that notation to mean the number of elements in an array. Okay, so this one is a fairly common thing because you have to get out of the array when you have exhausted and looked at every single element. The second condition to stay in the loop in this case is a bracket I does not equal to k. What that means is I have a value that I'm searching for. It is in variable k. So as long as a bracket I, which is the element that I'm looking at right now, does not equal to k, if both of these conditions are true, that means I have some other elements in the array that may have the value k, and I have not confirmed that none of them has the value k, then it's time to increment I so that I can move on to the next index and then do the same thing again. Okay, that's the search algorithm that we have talked about on last Thursday. Okay, what we're going to focus on today is this part here, just this part. The question is it okay to change the order of the conjunction? Now, in general, that is not the case. In general, you can change the order of a conjunction without changing the result. And I can illustrate why that is the case really easily using what we call a truth table. This is not the first time we have seen a truth table, but we'll use a truth table to make this point as well. Okay, so let's say we have two Boolean variables. One is called x and one is called y. And we want to find out whether x and y versus y and x are really the same for all possible combinations of x and y. Okay? When x can be true, when x is true, y can be true. When x is true, y can be false. When x is false, y can be true. When x is false, y can be false as well. Is everybody convinced that these are the only 4 possible combinations when x has to be a Boolean and y has to be a Boolean? Is that okay? Now this is a technique that you cannot use on regular algebra, because with regular algebra you have x being a number, integer or something like that, y being an integer. There's no way you can actually exhaust all the possible cases. But in the case of Boolean logic or Boolean algebra, the variables only can take up to 2 possible values. So you can exhaust all the possible cases and prove theorems this way, which is actually pretty handy. Now, by definition, true and true is true. Anything that has one side being false, at least one side being false, the entire thing is false. And same thing over here. This is the only case that is true. Everything else are false. So when you look at the 2 columns, x and y, and the column y and x, they are truly the same. For all possible input x and y, the output of the conjunction is the same regardless of the order. Okay? But here I am, saying that the order is actually important when it comes to programming. Okay? This is math, this is logic, and in logic they are the same. But in programming, they are not the same. In programming, they're not the same. Now this is that particular property, x and y is the same as y and x, is means it is commutable. You can actually exchange the order of the operands. But in this case, in programming, they are not commutable. Okay, and this is because we want programs to execute as quickly as possible. So when we go back to the previous slide here, when we evaluate this condition, if I equals to bar A bar, what happens is the computer executing this program will evaluate from left to right for sure. In other words, it's guaranteed to evaluate whether I is less than bar A bar first. Okay? If that is not the case, if I is already bar A bar and not less than bar A bar, what happens is the computer will automatically say that since one side, the left-hand side of the conjunction, is already false, there's no need to evaluate the right-hand side because the entire conjunction has to be false. Okay? So right then, the computer will exit and get out of the loop without even taking a look at the right-hand side. And that is a desirable behavior for 2 reasons. One, it is a little bit faster, okay, because when you get out, you don't have to evaluate the right-hand side. But that's not even the main reason. The main reason is when I does equal to bar A bar, if you try to evaluate the second condition, what happens? What are you going to look at on the right-hand side?
A number that doesn't exist.
An element that does not exist, because bar A bar is the number of elements in an array, but the index of the last element in an array is bar A bar minus 1. Now, if you do this in C, if it does evaluate the right-hand side, and this is a C program, what it will do is it will just go to some location that does not belong to the array, treat the value at that location as if it is an element in the array incorrectly, and in this case, it's not going to break the program, because if the first condition is false, it doesn't matter what the second condition is, the whole thing will still be false. On the other hand, if this is a Perl program, what it will do is it will create one additional element in the array. It will expand the size of the array by 1, so that now it does have that last element, which is also incorrect behavior. Does everybody understand why, in this case, we have to evaluate I is less than bar A bar first, and use it as a guard condition so that the second condition doesn't get evaluated when I does not have the proper value? Is that okay? All right. So if that is good, what we will do next is to say, but what if we don't have short-circuited evaluation? In other words, what if conjunction always evaluates both sides of the expression? What if disjunction always evaluates the both sides of the operator?
Wouldn't you have to throw an if statement in there?
You will have to throw in not only an extra if statement, you will need to use an additional variable so that you can isolate the two conditions. Okay, so we'll take a look at our old program. This is what we have already seen before, using the short-circuited evaluation. And then we'll have the other one using what we call a Boolean variable in order to make this work. Okay, so we'll take a look at short circuit 3 and see how this works. The first line is, it looks a little bit mysterious because up to this point I don't think we have seen anything like this. Have we introduced? Nope. Okay. But can anyone kind of give it a guess what it does?
It's saying that F is false.
F is on the left-hand side of an assignment statement. It is a variable, so we are changing the value of variable F. The right-hand side is just the value false, so that means we are changing the value of F to be false. Is that okay? Is that any different from our typical variables, which usually hold an integer? Other than the kind of value it is storing, it makes no difference. Okay. So are we okay with line 1? Do we need to revisit line 1? Line 1 is good? Okay. We can trace it too. We'll trace this algorithm when we're done explaining the overall thing. Line 2, there's nothing mysterious about this one. We start from the very beginning of the array, so I gets initialized to 0. And by the way, I only use I in this class because I, is a short, is an abbreviation of index. You can definitely use any other name for the same purpose in this type of situation. Okay. Line 3 looks a little bit mysterious now. We still have the conjunction, the little TP symbol in between, this part here. That's a conjunction symbol. Okay, it's mathematical operator conjunction. I just borrowed from the math symbol. We still have the first thing here, which is I is less than bar A bar. But the second thing that we have is not F. Okay, the little cliff symbol here means not the negation, and and we have F here. Is that okay? Well, since F as a variable is going to have a value of either true or false, that means I can also apply the negation operator on it. Not true is false, not false is true. So it actually works fine. I mean, there's no problem here. Are we understanding this part okay? Now, if you want to make sense of the variable names, I stands for index. If you want to give it a name for to variable f in this case, it is found. Okay, it is basically a Boolean variable to help me remember, have I found the value that I'm looking for. And it is initialized to false to begin with, because that's before I even look at the first element. So my assumption is, okay, let's just say that I cannot find it yet, okay, because I haven't even looked at a single element, so I cannot conclude that I have found it. That's why I have to initialize it to false. So what line 3 is saying is, the first part is saying, as long as I have not seen everything in the array, and the second part means I have not found the value that I'm looking for. Does it make sense that those two conditions should make me stay in the loop? As long as I haven't seen all the elements and I have not found it up to this point, I have to continue with the loop. Is that making any sense? Okay. So what do I do in the loop? The first thing I do in the loop is to do something like this. Now, once again, it looks a little mysterious because we are not used to seeing this kind of expression on the right-hand side. Well, can someone tell me what is the meaning of that expression? A bracket I equals k.
It does an evaluation if it's true, it returns true. If it's false, then it returns false.
Exactly. It evaluates whether those two values are the same or not. Okay, is it true or is it false that a bracket I, which is an element in the array, has the same value as k? And that is why in this class I only use the left arrow to mean assignment, and only use the equal symbol when I need to compare, because otherwise this will look awfully confusing. Okay, and what type of value does it give me? Just the highlighted portion of the statement. True or false? Okay, either true or false. I mean, it doesn't give me a number; it gives me a true/false value. What do I do with that true/false value?
It goes in those.
I use it to
F.
Yeah, I use it to update variable f. So f is going to be updated because of that. And I don't even use the value of f right away. I will use it when I get back to line 3. The next line, which is line 5, is going to increment I blindly to move on to the next element. I can do that blindly, it really doesn't hurt. I don't have to use a conditional statement to guard it, because when I get back to line 3, it will make sure that I get out of the loop in time. So I will never look at an element that does not exist. Yep.
What if the element you're looking for is at index 0?
At index 0, it will still find it. See, I was never meant to say, where is the element. We only need to know whether it is there or not. Do we have that element in the array? We're not looking for the actual index of the element. So that's a good question. All right. So we'll take a look and we'll trace this algorithm and find out, exactly how it works. Go to calc, just copy and paste the algorithm. All right. So we start with f gets false, I gets 0, while I is less than or a bar, and not f. Following, f gets a bracket I equals k, I gets I plus 1, while indentation. All right, so we have the algorithm copied, and just to be sure, let me save the file first. Make a folder for today. So 6. For some reason, I can't create a folder inside OpenOffice, so I have to do it outside. Oh, 06? Yep, 6. And we'll call this linear search. It's called linear search because we are starting from one end of the array and just increment the index as we go, as we continue to search throughout the array.
Thank you.
So in sheet 2, we'll go do the trace. got comments, line number, and we have 3 variables in this case, 4 to be exact. We have I, F, K, and array A. We can make array A relatively short in this case. We'll just make it have 2 elements because there's really no need to make it any larger than that. And then we'll go ahead and shrink the columns a little bit so we can see all at the same time. And then we'll start our precondition. Don't need anything. I don't need to know anything about I, nor F, nor K. Oh, actually, I do need to know something about K. I'll make K 5, and then in the array I have 1 and 3. Okay. In other words, the value that I'm looking for is not in the array. I have to make sure the loop does exit correctly, and I also want the answer to be stored in F because F remembers whether it was found or not. Okay. So we'll go ahead and start with line 1. Line 1 initializes F to false. So we'll just say this is false. And then on line 2, we initialize I to 0. We start looking from the beginning of the array. Comments in this case needs to be a little bit wider because our condition is a little bit longer this time. Also make the entire window a little bit wider too. Like that. I is less than bar A bar. Is that true or is it false? It's true. I is 0. What is bar A bar in this case? It's 2 because we only got 2 elements. So 0 is less than 2 is true. Do I have to evaluate the right-hand side of the conjunction? No. Because it's a conjunction, one side being true means it can still be false if the other side is false. So I still have to evaluate the other side. What is the value of the other side? Not F. What is F? F is false. What is not false? True. So now we have true, and which means the entire thing is true. We go into the loop here. We go to line 4. Okay, we'll take a look at what line 4 is going to do. Line 4 is going to evaluate the right-hand side first. The right-hand side is comparing A bracket I to K. I has a value of 0. So A bracket I refers to A bracket 0, which has a value of 1. It's comparing that to K. K has a value of 5. 1 equals 5 is false. So we have to update F with a value of false. So even though it's the same value, we still have to remember that we potentially could have changed it here. So I still make this cell stand out like that. And then we go to line 5. We add 1 to I goes from 0 to 1, and then we go back to the beginning of the loop. I at this point has a value of 1. Bar A bar is 2. 1 is less than 2 is true. We cannot conclude the actual value of the conjunction at this point. We have to evaluate the right-hand side. F has a value of false. Not false is true. So we have true and true again. The entire thing is true. We go to line 4 again. Line 4 is going to compare A bracket I with K again, but I has changed. So we are not looking at A bracket 0 anymore because I now has a value of 1. We are looking at A bracket 1, which has a value of 3. We compare 3 to 5 and ask, are they the same? Nope, they are not the same. So that means the answer is false again on the right-hand side of the expression on line 4. So that means F is updated to false again. Then we go back to line 3. Oh, we forgot line 5. Line 5 is going to add 1 to I. I goes from 1 to 2. Then we go back to line 3 again. Now this is where things are important because in this case, I has a value of 2. Bar A bar has a value of 2. 2 is less than 2 is false already. And then we conclude it is false. We don't even mention the right-hand side because I want to emphasize the fact that we don't need to evaluate the right-hand side of the expression to come to the conclusion that the entire thing is false. Are we doing okay with this trace? The first part is really kind of boring other than the part that we are using a variable to store a Boolean value. That's something that we haven't seen before, but it's not really that tricky because a variable is a variable. You can store just about any value in a variable. So after line 3, there's really nothing to do. We get to post and we are done. So in this case, I just made a mistake here. What is the whole point of this exercise? I just forgot about that part. So let me erase this part here and also erase this one. This is the last part that I made a mistake here back on line 3. The whole point of this algorithm using an extra variable is to do what? To do the same thing as the other program that made use of short-circuited evaluation, but this one will work without short-circuited evaluation. Remember that? That's the reason why we're even talking about this program. So I actually made a mistake here. I have to evaluate both sides in this case. I is less than bar A bar is already false, but I cannot get out at this point because I just want to illustrate there's no harm in evaluating the right-hand side either. Because in this case, does the right-hand side make use of I as an index into the array? No. In other words, I have just isolated the indexing operation, which is now on line 4, from the condition of the loop, which is on line 3. And therefore, even if I don't have short-circuited evaluation, this program would not do something wrong. It will still be correct with or without short-circuited evaluation. So to complete this, I will have to say this condition is false because I is less than bar A bar is false already. But in this case, it doesn't hurt to evaluate the right-hand side of the conjunction, and we'll still get to post. Are we doing okay with this example, this particular trace? Does everybody understand the fine point that I was trying to make here? Why I said that I made a mistake when I said, oh, we don't have to evaluate the right-hand side. Yep.
Can you just run through us a program if we're in the same, but without using F, or without using 2 variables, with using one where it would short circuit and then
Sure,
fail?
yeah, we can do that.
See them side by side.
Absolutely. So in that case, let me see what I should do here. I'll just make a new file, okay? I can probably just recycle the one from last Thursday because I think we did one on last Thursday. I can just retype the program too. So I gets 0, while I is less than bar A bar, and A bracket I does not equal to K, do I gets I plus 1, and while, and then fix the indentation here. Okay, so I'll keep those windows open. I was just thinking whether I should close those windows. I'm not going to close it so we can see it side by side later. And I'm going to save this file as linear search with short-circuited evaluation. All right. Comments, line number. We only have one fewer variables because I have I, K, and then A. I would use exactly the same case here. A is going to have 1 and 3. K is 5. Shrink those columns a little bit. Merge these two. It's just making it look nice. I mean, other than that, there's nothing that is important. There we go. All right, so we have exactly the same precondition. Line 1 is initializing I to 0. Line 2 in this case is evaluating I is less than bar A bar. It is because 0 is less than 2. And in this case, the array indexing is on line 3 as opposed to, on line 2, excuse me, as opposed in the other case, we do not have the indexing operation on the same line in the while condition. Okay, so this is the main difference here. Okay, so now we have to evaluate A bracket I versus K. I has a value of 0 at this point. A bracket I refers to A bracket 0, refers to column E, which has a value of 1. We compare 1 to 5. 1 is different from 5 is true. So we have true and true. The whole thing is true. I Are we doing okay so far with this? Okay. Then we have no choice but to go to line 3. Line 3 adds 1 to I becomes 1. We go back to line 2, we evaluate those conditions again. I is 1, bar A bar is 2, 1 is less than 2 is true, but that's not enough reason to get me out of the conjunction, because when one side of a conjunction is true, the conjunction can still be false if the other side is false. So we have to evaluate the other side in this case, which is A bracket I, but I this time is 1, so A bracket I refers to A bracket 1, column F has a value of 3. We compare 3 to K, which is column D having a value of 5. 3 is different from 5 is true. We have true and true, so the entire thing is true again. We go to line 3, we add 1 to I goes from 1 to 2. We go back to line 2, and this is where things get interesting, because I is now 2, bar A bar is also 2, 2 is less than 2 is false already, and we do not evaluate the right-hand side. That's what we mean. Yeah, go ahead.
It didn't short circuit and continue to evaluate the conjunction. That's
Right.
when things go wonky.
Exactly.
Something that doesn't exist.
Because if it is not short-circuited, then we would have done something wrong. We would be either looking into a location that does not belong to the array and treating it as if it is a part of an array, extend the size of the array by 1, or it would have generated a runtime error in the case of a Visual Basic program. It would have complained, we are indexing the array out of range. Yep, go ahead.
So in this example, the operations cannot be reversed, but in the other one they can be?
Correct. Whenever your programming language supports short-circuited evaluation, it is not reversible, it's not commutable anymore. You cannot exchange the order of the operation. And all programming languages that I know of, all modern programming languages, have short-circuited Boolean evaluation. So when you use it in Visual Basic, PHP, Perl, Python, C, C++, Java, you name it, almost all programming languages use short-circuited evaluation. Okay, and just to finish this, when the condition becomes false, we get to post. Now in Visual Basic, they make it kind of confusing because they also have a non-lazy or non-short-circuited evaluation for Boolean operations. I think and also or else are the two operators that override the default behavior of using short-circuited evaluation. In fact, we can just take a quick look here, and then we'll just search for Visual Basic or else and also. I think those are operators. Okay, VB.NET features two logical operators that help make your programming more logical. Well, what does that say about the previous versions of Visual Basic? The new operators are and, also, and, or, else, and they add a lot more to the old and, or operators. Okay, so I was wrong. I got it reversed. In Visual Basic, the usual and the usual or are not short-circuited. If you want it short-circuited, you have to use and also and or else. Okay, so these are the short-circuited operators. The ones with just the AND and the OR are the non-short-circuited operators. So once again, Microsoft has its own standard, on things that is completely different from everybody else's. Being different is okay. Being opposite is a little different. So I'll be doing okay so far with short-circuited Boolean operator evaluation. No questions? Okay. So when we move up, I just want to make sure I don't miss anything here. Okay, that's it. That's the whole module. So some of these modules are really short. It's not very extensive. This one is interesting. Okay, searching in a sorted array. It's interesting because I just want to look at this one here. just look at this frame and not the other one. There we go. All right. Okay. The first thing is, what exactly is a sorted array? This slide doesn't serve any purpose other than making sure that we know how to express, whether an array is sorted or not. So we'll take a look at this, just quickly. So this part here says assume the array is already sorted in a non-decreasing order. Now there is a difference between non-decreasing order versus increasing order. The difference is whether elements can have the same value or not. When I say an array is sorted in an increasing order, that implies that you cannot have the same value, because if two elements have the same value, they're not increasing. When I say an array is sorted in a non-decreasing order, that means the entire array can have one single value, because as long as it's not decreasing, it's good. Okay, so it can be increasing or it can be the same. In this case, I have an array that is sorted in a non-decreasing way. So how do we state that? How do we use mathematics to express that? So the way we express it is like this. A bracket I is less than or equal to A bracket I plus 1 for I going from 0 to n minus 1. And n in this case is bar A bar. Now that is actually wrong. Why is that wrong? I actually have to fix my note here. This should have been n minus 2. Why is it n minus 2 and not n minus 1? Think about the end case here. When I equals to n minus 1, this becomes n minus 1, which is fine, because n is the number of elements in the array, which is bar A bar. Bar A bar minus 1 is a valid index. What does it make this one? It becomes bar A bar, because bar A bar minus 1 plus 1 is just bar A bar, which is out of the range of the array already. So I really should fix it. I can probably fix it right now.
It's only HTML.
No, it's not HTML. I'll show you guys what it looks like.
Okay. Now we have username.
Yeah.
We can all start reinforcing the server now.
Okay, so this is in module 60, and this is how I type my class notes. This is the tool that I use. It's called VI. It's a very classic but popular editors for developers or programmers. And this is called LaTeX. This is, you can see this is, it doesn't even resemble, like a regular text document. So this is called LaTeX. And we have to look at this part here. Backslash LE stands for the less than or equal to symbol, LE less than or equal to. This is how I type everything. And to fix it, I'm going to change this n minus 1 to n minus 2. Now, when I exit, I'm only changing the source document here, and it needs to be converted using different tools to generate the HTML and also the PDF documents that you can look at, that you can download. So the first thing I have to do, the next thing I have to do is to say publish, which will do two things. It will actually convert the files. It will also upload the file from my authoring machine to the publication machine. So there are two different machines. One only stores the source, and the other one stores the version that you can see when it's published. And I think it's stuck in a loop of some kind.
Control C.
Yep, Control C breaks it out. Let's see, it's stuck in the loop. I'll just do it manually. Okay, so now we can do the other one.
Fail.
No, it's not failing. It's actually generating the bitmaps. it's regenerating all the bitmaps. That takes some time. I can just do it manually as well. So we'll do a tab HTTP. Let's do it again. And this one will synchronize the files from my publication machine to the files on my authoring machine. So any file that has been updated will be synchronized. So now we can go back to our notes here, do an update. Okay, control update, shift update. Let's reload this one first. Okay. It actually used a new standard. I forgot about the new one. There we go. Much better. Yep, I'm using very archaic tools. You know, it's not WYSIWYG.
You know what?
At
As long
all.
as it works, who cares?
More text spaces is better.
Well, LaTeX was originally invented for formatting math stuff. It was invented, you know, just to deal with math publications. And guess who wrote, you know, LaTeX or TeX, TEX? Okay, TEX, you know, is quote unquote the name of the tool, but it's actually not pronounced text. It's actually tak, because it is in Greek. It's tau epsilon chi. Yep.
Did you want to change the other example to n-2 to the right?
You mean the other
I
one?
mean, it says you can also split those source out as.
Okay.
Now I gotta do it all over again.
Good job.
I'm just saying.
Well, that's a good point. Just gonna.
I just noticed myself.
Okay, let's reload it. It's still showing it. Oh, okay. It's still showing it because I have only removed it in the local version, so now I have to synchronize it. And if I reload it, the other one is gone. The only one that is left has the n-2. Okay. All right. So are we doing okay so far with this? I know it's a distraction, but I kind of want to show you guys the tools and, you know, all the fun stuff too. Any questions at this point about how we express that the array is sorted in a non-decreasing order? Is that good? Does anyone know how to do this using pure mathematical symbols? I use a whole bunch of English words here. Does anyone know this symbol?
No.
Or this symbol? No? Okay, well, you will see these symbols probably by the time you get to CISP 440. One is, yeah, go ahead.
The n-1 at the end.
And this is correct.
Okay.
Yeah, that one is correct. We just have to fix this one here, because when I equals to n-1, then this becomes a bracket n-1, excuse me, n-2. When I is n-2, then this I becomes n-2, but this one, because it's I plus 1, it becomes n-1, which is actually correct, because n-1 is the last value index in an array, in this case. Okay. All right, so now that we know how to express that an array is actually sorted, we will go ahead and take a look linear search again. The problem with this tool is it took away all the indentations, so it just looks a little bit awful when we have to refer to the indentation. Okay. This part here looks almost identical to what we have been talking about since the beginning of this class. Does everybody recognize, other than line 3 does not have the proper indentation, that this is identical to what we have been talking about since the beginning of the class, you know, for the discussion of short-circuited evaluation? The only part that's different, oh, well, this is actually identical. If an array is sorted can we do a little bit better? In other words, let me give you an example using my little text box here. Okay, if my array is sorted, having the values, okay, I'll just give you some examples. 1, 1, 3, 10. Okay, these are the values in the array. If I'm looking for, let's say, 2, okay, when can I get out of the loop? I compare 1 to 2, okay, can I get out at that time? Can I guarantee that 2 cannot be in the rest of the array? Not yet, right? I compare 2 to the second one, can I get out at that point? No. I compare 2 to the 3, 2 does not equal to 3, can I get out at that point?
Yes.
I can, because if the array is sorted in a non-decreasing way, what is guaranteed? All the other elements are greater than or equal to 3. If 3 is already greater than 2, which is the value that I'm looking for, then that means also the rest of the array cannot be equal to 2 either, and therefore I can get out early. Yep.
If it was 1, 1, 2, 2.
If it's 1, 1, 2, 2, then you cannot get out early. You actually have to look at the entire array before you can get out. But that makes sense because when you're only comparing 1, 1, 2, 2, if it's 1, 1, 2, 2, by the time you get to the first 2, you get out because you have just found what you're looking for.
Then it'll go with the first one, not the second one.
I only need to know whether it is there or not. I don't need to count how many of the 2s we have. Okay. All right. So based on this observation, I can do a little bit of optimization. In other words, I can change the condition just a little bit so that instead of saying A bracket I is different from V to stay in the loop, I can just say that as long as A bracket I is less than V, we can stay in the loop. So that means I can get out of the loop when A bracket I equals to V or when A bracket I is greater than V. And that's why we have a second statement here, a conditional statement that says if I equals to bar A bar or A bracket I does not equal to V, then we can conclude no element in A has a value of V. Does it? Yep, go ahead.
What's the difference of the up arrow and the bottom, the down arrow?
Sorry? That's because it is an OR. This is not a conjunction. This is a disjunction. This is an OR. Okay. Now, does it make sense though? Okay, let's just focus on the first part here. Does it make sense that I can conclude no element in array A has a value of V if any of one of these two conditions is true? Does it make sense? Well, let's take a look at the first one. What does it mean when I equals to bar A bar? We have gone through the array and we could not exit early because we have found it. So that is good. That's a good reason to conclude that no element in A has a value of V, because otherwise I would have exited with I being the index of the element that has the value of V. The second one, when you look at the other part of the disjunction, is A bracket I does not equal to V. Now, we have a problem here, don't we? How do we know that I is still a valid index into this array? Won't we get into the same problem that we talked about a little bit earlier, that I can be bar A bar already, and so when we try to do A bracket I, it is trying to index an element that is not in the array. Well, remember short-circuited evaluation? Well, before we have only talked about short-circuited evaluation for conjunction. This is a good chance to talk about it for disjunction. If I does equal to bar A bar, this would be true, right? With a disjunction, if one side is true already, do we have to evaluate the other side? This is an OR. With one side being true, do we still need to evaluate the other side? No, because at least one side being true means the entire thing is true. So that means if I does equal to bar A bar, right at that point I can conclude the entire expression is true, and then I'll just go ahead and make that conclusion. Yep.
I have a quick question. Given the code that's up there, how do we know how many elements are in the array?
Bar A bar. Bar A bar is an expression that returns.
Oh, no, I know that. How do we know how many elements are in the array? Bar A bar doesn't tell you how many elements are in the array at the time right now? Is there a precondition we didn't see, or?
The bar A bar returns the number of elements in the array.
Okay, so how many elements are in the array?
We don't have any preconditions.
We do not have a precondition yet.
Okay, that's what I was asking.
Oh, okay.
Yep.
So you can only know when you're tracing it with an actual test case. Okay, I misunderstood your question. Okay, so now, so that means that by the time we evaluate this condition, what has to be guaranteed based on our observation of short-circuited evaluation? The first condition has to be either true or false. Which one does it have to be? False. Has to be false, because if it were true, we would not be at this point. If I does not equal to bar A bar and it started off from 0, what does it mean? I is less than bar A bar. If I is less than bar A bar and it is at least 0, that means it is a valid index. And that means, this will be fine. I will be accessing an array element that is actually in the array. Is that working out okay? Okay. Now, why would that make me conclude that no element in A has a value of V just by looking at one single element? If I just confirm that one single element does not equal to V out of the loop, how can I make that conclusion for sure?
Because in line 2, you evaluated the A sub I was less than V. So
Exactly.
it's not equal to V and it's not less than V because it's an array is sorted. It
Exactly.
can't be equal, or V can't exist.
Exactly. That's exactly the case. Basically, it's because we would have stayed in the loop if this condition was true. Okay, as long as that condition is true, we would have stayed in the loop. We already know that I does not equal to bar A bar because I said it in this particular case. Let's assume I does not equal to bar A bar, which means I has to be less than bar A bar. If I is still less than bar A bar and I'm out of the loop, what has to be true? Or what has to be false in this case? That has to be false. That would be my only reason to get out of the loop early. If I get out of the loop early, that means this condition is false. A bracket I is greater than or equal to V. Right? When I get down to here, if I can confirm that A bracket I does not equal to V, it can only make one single conclusion based on the exit condition. A bracket I is actually greater than V. If A bracket I is greater than V already, I can guarantee all other elements in the array are also going to be greater than V, which cannot be equal to V, so I can make a conclusion that no other element in array A can have the value of V. Is that making any sense? Kind of? Okay. The else corresponds to this condition being false and this condition being false, which means I did find an element in array A that has the value of V. Okay. So with this optimization, what kind of speed up am I looking at? Let's say we have an array of 1,000 items, and I'm looking for items in a truly uniform random way. In other words, the chances of looking for the first element is the same as the chances of looking for the last element. And let's say that we are not even looking for things that do not exist. We're only looking for things that are in the array. So with this optimization, what kind of speed gain am I looking at? Zilch. Okay, if you're only looking for items that are in the array, there's no speed gain. This will only gain speed if you're looking for things that are not in the array. Okay, so fine. Let's say we're always looking for things that are not in the array, and it is also uniform. Okay, what kind of speed gain am I looking at on the average? I'm saving 50% of the execution time. Okay, is that a lot of time?
Yeah.
Yeah, it's good, but not as good as the next algorithm. Not even close. Okay, so let's take a look at the next algorithm. Are we okay to move on? I mean, does everybody understand this little optimization here? All I did was to change the comparison from the original not equal to or less than or greater than to just less than. In other words, I give myself one more reasons to get out of the loop. Okay. Let's look at binary search. But before we even talk about binary search, let me ask you a question so that you can tell me approximately what you think it would be the answer. The world population is what, 6 billion something right now? 7? Okay. Let's say it's 8. Okay, let's say the world population is 8 billion. And I have a master directory of every single person on Earth. Okay, every living person on Earth, is in this directory. And let's just say that we have some kind of ID for everybody in this directory, and I'm searching by that ID, and it's sorted by the ID. 8 billion items. How many times do you think I have to search? How many times do you think I have to compare a particular ID that I have to a particular ID in the array before I can either conclude that ID is in the array or that ID is not in the array? Worst case scenario.
Every single time.
8 million.
8 billion? But what if I tell you the array is already sorted? Can anyone give me a guess, like,
You only have to search it once because you can go to that number.
Sorry?
Let's say everybody has an ID number.
Mhm.
It starts from 1 to whatever the highest number is. You can go to that line in the
Okay.
array and find it.
But what if it is not sequential? So everybody has an ID, the ID is not sequential, but the array itself is sorted.
How would the array be sorted?
It's sorted by the ID number, but the ID number can be just randomly generated. Okay?
Wouldn't you just check the digits?
You can check the digits?
Of the ID number, just one digit, and then once it meets that requirement, then move to the next one. And
But how do you know where the next one is in the array?
Oh yeah.
Remember, in the array, you kind of have to look at it from the perspective of the computer. At any time, you can only examine one particular element in the array. So you have a very small peephole into the entire array, and that's your limitation. Yep.
You take a look at the first 4 or 5 digits and see if it matches within your array. Break it
Okay,
down from
you look at the first 3 or 4 digits and see how it matches what. Remember, you have a little peephole, okay? You have a huge array, but a tiny little peephole that you can only look at one item at a time. Go ahead.
You could take the halfway point
Okay,
and then see if it's greater than or less than the halfway point.
yep,
If it's less than, you go to the first half, and then you look at that half.
and do the same
Do
thing.
the same thing and repeat.
Okay. So using that particular method, how many comparisons do I need to make a conclusion? Either it is there or it is not there. We have 8 billion items to begin with. It's 33.
Wow, you know.
33. We just need 33 comparisons in order to make a conclusion out of an entire directory of 8 billion items. Yep.
But how are you able to make that comparison in the first place? Like, if you don't know how, I don't know.
The comparison is only, okay, when I said the number of comparisons, I'm referring to comparison to a particular element in the array. So if I have the index of that element, I can just pull that particular element out and say, okay, yeah, let's compare what I'm looking for with this particular element in the array. Okay? So let me ask you another question. What if world population doubles to 16 billion people and we have to colonize Mars and a few other planets?
34.
Then it moves on to 34. Very good. So every time you double the size of the array, you only have to add one more comparison. Now, I think that is pretty cool. That is pretty efficient. Okay? Let's take a look at how it works. Yep, go ahead.
How is what I suggested different from what he was saying? Because I was thinking the same idea. I was just thinking instead of the whole block cutting in half, just the digit spaces versus the listing itself.
But in order to find out which entries in the array would match the digits that you're looking for, don't you need to examine those elements? But his approach does not need to look at the elements. He's picking out only one element out of the entire stack, the one that is right in the middle, and only have to make one single comparison. Then we have the information to go either one of three ways. One, this is what I'm finding. This is my lucky day. I find the item that I'm looking for out of 8 billion items in the first comparison. Unlikely, okay? But the other two alternatives are really good too, because what I'm looking at is either greater than or less than what I'm looking for. So I can either chuck the first half of the entire 8 billion entries, which means I can chuck 4 billion entries, the first 4, or I can chuck the other 4 billion entries. Either way, I have just reduced the number of items that I have to sort through by 1/2. Okay? Yep.
What if the 8 million items were like random hashes? Could you still use that method?
That won't work because a binary search only works in sorted arrays.
If it's sequential.
It has to be. It doesn't have to be sequential as in 1, 2, 3, 4, 5, but it has to be sorted in the sense of 1, 5, 6, 8, 11, 20, 21, and so on. It has to be sorted. Okay. And then of course then we have efficient sorting algorithms to make an unsorted array sorted to begin with. Okay. So we'll go ahead and take a look at an example first. I'm not sure whether we have enough time to actually write the algorithm itself, but we'll go through an example first. So what we'll do is we'll use a spreadsheet for this purpose, and I'll give myself some elements, and we have to make sure these numbers are sorted. So we'll start with -5, -3, and you can even have duplicate entries. Duplicate entries do not hurt binary search. It's fine as long as it is still sorted. So we have 0, 1, and then we have 2, 2, 7, and then we have 12, 13, 19, 20. Now I have to be careful, what is the total number of items, because certain numbers work out better than others. 25, 29, and
So powers of 2 work better. Powers of 2 work better.
Actually, powers of 2 minus 1.
Okay.
Because powers of 2 means you have an even number, then it's kind of. I don't want to talk about the middle element for that in that case yet. Okay, so we'll talk about just 2 to the power of something minus 1. What is 15? How is 15 related to that? It's 2 to the power of 4 minus 1. Okay, so this will work out really well.
It's a binary number.
It's
It's binary.
well, in a binary, as a binary number, 15 is 1, 1, 1, 1. It has all ones. Okay. So what I'll do is I will also have to tell you which number I'm looking for. So I'll say look for. Okay, do you guys want to look for something that is there or look for something that is not there?
Just look for something that's not there.
Okay, look for something that's not there. How about -4? I think it looks kind of tricky because -4 is right at the beginning, and we have 2 -3s. -4 looks okay. So let's look for -4. Okay. Binary search works by comparing what you're looking for, -4, with the middle of the section of the array that can still potentially have the value. At this point, before the first comparison, which portion of the array can potentially have a -4? The entire thing, right? Because before the first comparison, I don't know, which part I can rule out. So this is all about what can you rule out. Okay. So out of the entire array of 15 elements, which one is right in the middle of everything? Okay. This entry is right in the middle. So we'll go ahead and make a comparison and make a conclusion. We say -4 is less than 7, which makes sense, right? Now, okay, let's see whether we can do this. I have to, come on. Okay, paper. Oh, the wrong cell. Okay, -4 is less than 7. There we go. I know I can escape it somehow. Okay, so we know that this particular entry needs to be ruled out. But what else can we rule out in this case? We're looking for -4.
Everything beyond that.
Then everything below that too,
Yeah.
right? So this element and everything below it. What I'll do is I would use like a highlight, to indicate which portion of the array I can rule out. So we'll just go ahead and format cells, change the background color to, let's say, just a boring gray color. to indicate these cannot have the value that I'm looking for. So what else can possibly have -4? The first 7 entries, right? I will do the same thing with the first 7 entries. Find the middle element of the first 7 entries and do the comparison. Which one am I comparing this time? Which row number? 4. Row number 4. Okay, so this will be the next one I'm looking for, or the next one that I compare to. So we'll come to the same conclusion. -4 is less than 0. That means this element can be ruled out along with everything after that. Okay. So we'll go ahead and do the same thing and just rule out the parts that we can rule out. Now we have how many elements left? We have 3 elements left. Out of the 3, which one should I compare to? Okay, the one on row 2. Okay, so we'll say -4 is, oops, I got to escape it first. -4 is less than -3 is true, right? So that means this element can be ruled out along with everything that's after that. Okay. So we'll go ahead and rule all those out. Are we done yet?
No.
We have one left. Where's the middle part of this part of the array? Itself, right? Because we only have one element left. So now we can say -4. -4 is not equal to -5. It is greater than -5. And so we can rule this one out. And also everything that is above it. Well, that turns out to be nothing above it. But that's okay. We can still say that this is now ruled out. Okay. At this point, are there any elements in the array that we have not ruled out? No. They have all been ruled out. So my conclusion is
There is no
there's no -4. All right, very good. So let's go through another test case here because we want to be very comfortable doing this by hand first before we write our algorithm. Do you guys want to do something that's right in the middle that is not there? Maybe a 3? Would that be okay? Because a 3 is kind of tricky because we know how we can rule out everything on one side, but let's look for a 3. Okay. Which one do I compare to first? Same thing. We compare to the one on row 8. So the conclusion this time is 3 is less than 7. Okay. What can I rule out knowing that 3 is less than 7? Okay, everything that's after we can rule out. So we'll say format cells, change the background color, so these are no longer eligible. So we only have the first 7 being eligible elements. Which one do we compare? Row 4. Okay, row 4 is right here. And the conclusion is 0. Oops, excuse me. 3 is greater than 0. And what is that telling me? I can rule out this cell for sure, but what else can I rule out?
Everything above it.
Everything that's above it. Very good. So now we can highlight this one and also everything above it and say, oh, okay, those are all ruled out at this point. I have 3 elements left, which is 5, 6, and 7. Out of these 3, which one is in the middle? 6, okay. So we compare against this one. 3 is greater than 2. So that means it does not equal to 2. I can rule out this one, but also everything above it. Very good. So we have these ruled out. And now how many elements have I left? I only have 1 left. I still have to compare because I really don't know the value of this element. I have to compare to find out what it is. So this is my last comparison. 3 is greater than 2. That means this one is ruled out along with everything that is before that. But at this point, everything is ruled out. There's nothing left in the array for me to consider. I'm done. Now, is that matching, the rule that I was talking about? With 8 billion items, you need 33 comparisons.
Yeah.
I actually lied. You need 34. Because if you look at this one here, the number of elements is 2 to the power of 4 minus 1, and we need up to 4 comparisons. 8 billion turns out to be 2 to the power of 33, so we'll need 34 comparisons to deal with that case.
But one less than 8 billion would be under 30.
Oh, that's right, it will still be 33. Did I say 33 or 32? I said 33, oh, 33 will still be right. Okay. All right, so are we feeling comfortable doing this by hand? Okay. Now we have about 3 minutes left. So what I'll do is not really to talk anymore about the technical stuff. You should probably review this as much as you can so that you feel comfortable with the logic of binary search. What we are now getting into is, this is called, okay, does this look efficient to you compared to linear search, starting from the beginning and just go by elements one by one? This is what we call time complexity. Time complexity is basically just a relationship between the size of the problem, in this case it would be the size of the array, as opposed to how much time it takes to solve the problem. In this case, how many iterations do we need, how many comparisons do we need to come to get to the answer. That's called time complexity. It's really just a relationship between the size of the problem and how much time it takes to solve the problem. Do you think that's an important topic? Do you think that is something that programmers should be aware of?
Yes.
Yeah.
Okay, and you're absolutely right that this is an important topic. It is no big deal if you cannot remember a particular algorithm, because we have Wikipedia. So as a programmer, when you get out and actually get a job, you can go to Wikipedia and say, oh, I forgot about a particular search algorithm. Let's say bubble sort. Okay, you're looking for a sorting algorithm. You have bubble sort and you have heap sort. Okay, so we'll look for heap sort here, and Wikipedia is a fantastic resource because it will tell you what it is. It will give you the pseudocode and so on and so forth. But it will also give you these really odd looking things. It will give you the worst case performance, best case performance, and so on and so forth. And they use kind of like a strange big O notation. This is actually the technical name is called a big O notation. Okay? And in this case is n log n, big O of n log n. What exactly does it mean? Now let me just look up one more entry and then we'll call it a day. We'll look for bubble sort from Wikipedia. And it has a different number. It has a different function. This one has a worst case performance of big O of n squared. Okay, and the first one, heap sort, has a big O of n log n. Okay. This doesn't seem to be very important to me. As a programmer, I'll just pick the algorithm that is the easiest to implement, right? Especially programmers working for certain companies would definitely use that approach. Look at heap sort here. This is the pseudocode of heap sort. Does that look simple to you? No, doesn't look simple to me. Look at bubble sort. Pseudocode. Hey,
I like that one better. It's less typing.
Exactly. Just copy, paste, and be done with it, right? Okay, so on Thursday, I'll give you the scenario where a software company is downsizing and they only want to keep the best programmers in the company. And I'll give you, the scenario is I'm the old timer there. I'm still using my 386 computer in the company because that's my machine. My new colleague has a Pentium, i7 based, desktop computer, and the boss says, okay, I'll give you guys problem to solve. Whoever can solve the problem faster on his or her computer gets to stay in the company. So you would think that I'm at a very bad disadvantage because I have a 386 machine with only how many megabytes of RAM in those days?
We're talking K.
We're talking 512 megabytes or so. Okay, and my colleague has an i7 with 16 gigs of RAM in it. Okay, so let's see on Thursday. We'll see who gets to stay with the company. And why?
Yeah, that was just cooking.
Choosing algorithm.
Yeah, 450 megahertz.